Good morning, all. My name is Isha Goyal, and I'm one of the team members under CSIR Jigyasa program. I would like to welcome all the scientists along with our special speaker, all the school students and teachers, and everyone joining the webinar. As we all are aware of the CSIR Jigyasa program, which conducts various activities to enhance the scientific knowledge among the school students. This program focuses to connect school students and scientists to extend the students' classroom learning with a planned research laboratory based learning. Under this program, CSIR is organizing webinars as Let's Talk Science Series 2.0 in collaboration with India's Chandigarh chapter. So before starting our lecture, I want to convey that our lecture is live on CSIR Jigyasa YouTube channel. You can also there. Today we have with us Surjit Kaman, scientist SCIR CSIO Chandigarh, in the Department of MSSA. He'll be delivering lecture on lasers and its application in the sensing. There will be question answer session at the end of the lecture. Kindly put your questions in the comment section in the YouTube, or you can ask your questions here in the Google Meet, here at the meet and the end. So over to you, sir.
Yeah, thank you, Isha. Am I audible?
Yes, sir.
Okay, so let me share my presentation. Is this on full screen? Can you see my presentation?
Sir, your presentation is not visible. Kindly
I guess.
share your screen. Yes, sir.
I think your voice is not very clear. Uh, is it visible now? Can you see my slides, Isha?
Yes, sir. We can see your slides.
Okay, sorry for this glitch. A very good morning to everyone, and thank you, Isha, for your kind introduction. And today I'll be talking about the laser and its applications in sensing. So myself, Surjit Kaman, working as a scientist here in Material Science and Sensor Applications, CSIR, CSIO. So these are the topics that I will be discussing during my presentation, and about the CSR, CSIO, laser introductions, working principles, types of lasers, laser operating modes, safety classifications, and applications of lasers. So I would like to brief about the organizations that I'm working, that is CSIR, CSIO. So CSIO or Central Scientific Instruments Organizations is a constituent unit of CSIR, Council of Scientific and Industrial Research, based in headquartered in Delhi, and it's a premier national laboratory dedicated to research, design, development of scientific and industrial instruments. So as you see, we have various verticals in our R&D group. There's imaging, avionics, display system, IIDS, manufacturing science and instrumentations, biomedical applications, material science and sensor applications, intelligent machines and communication systems, energy management technologies. There is a Chennai-based center. So these are the verticals, and these are the horizontals: business, BDPM, industry connect, information service divisions, ISTC center that runs a diploma course through our institute. So it's based in Sector 30C, Chandigarh, and everyone is very much welcome to visit this institute in future. So moving on to my talk. So I think everyone has heard about laser. So the history of laser goes back to 1960 when Theodore Harold Ted Myman, who first discovered the laser. He was an American engineer and physicist. So I think everyone has seen lasers, the pointers that we see for various applications. So what does actually laser mean? So laser is an acronym for light amplification by stimulated emission of radiations. So it's has various characteristics like the coherence, directionality, monochromatic, and high intensity. So I'll go back into details, more into details of these characteristics. And as you can see in this picture, this was the first laser that was discovered by Myman, and it was the first ruby laser. So as you can see from this picture, what are the laser characteristics? So what defines the lasers actually? So so it has to be a coherent. So as you see from these pictures, it has an incoherent light, which has different phase relations with that. And if you see that the right pictures is a coherent light wave, so it has to be a very coherent. So this is one of the special characteristic of laser. And the second is the directionality. So as we see from this from this image, we can see the first is incandescent torchlight bulb, how it is direction is very much in a broader form. But here in this, in terms of laser, it is very specific and very targeted to and very small beam size. So this has to be a very directionality property has to be there. And the third is that monochromatic and high intensity. Monochromatic is like, as we see from this picture, there's as we see from the regular light, the light has different wavelengths. All the wavelength combines together to form that white light. So it has to be suppose if I go for the second image, it has, if we put a filter in there, as a red filter in there, then we can see that only that what's called that particular simple single wavelength. But in terms of lasers, it emits a light of only one wavelength, and that's how it is different from that other normal incandescent sources, light sources. Moving on to this, how actually this laser works. So this the principles of working of laser. In lasers, the photons are interacted in basically three ways with the atoms. One is absorption of radiation, spontaneous, and that stimulated emission. Okay, so here in this picture, we can see that what is actually an spontaneous emission. So any, we know that in an atom, the electrons have a different energy levels. The electrons that are very near to the nucleus are the lower energy level, and as it move away from that nucleus, it is a higher energy state. So based on that, we take this, as we see from the second image, assuming that there's two energy levels. One is the lower energy level, that's E1, and is the higher energy level, that's E2. So whenever an energy strikes an atom, the electrons from the lower energy state moves to the higher energy states. And how will that be possible? That only will be possible when an amount of energy equal to the difference between these two energy levels, E2 minus E1, strikes that atom, so that the electrons will move up to the higher energy states. So as we see that in spontaneous emissions, so as the electrons move away from the lower energy state to higher energy state, so and after that, it has got a definite lifetime of staying in that higher energy state. So as soon as it loses, it falls back and tries to come back to that lower energy state. So during this process, so it emits an energy in terms of photon. Photon. So this process is called the spontaneous emissions. So the next process is like, what is this stimulated emissions that is required for this lasing operation to happen? So as this lasers, was the electrons comes falls from the higher energy state to the lower energy state, and assuming that it strikes another electron that's already there, so it will create more number of electrons during this process and release more energy. So this is how actually the lasing happens. But practically, it's very not possible to generate to see lasing with a two-state energy level. So we need a population inversions to happen. And what is this population inversion? So it is a process where we created a state that is called a metastable state, where we stored electrons from the high energy state to fall and store that and increase the populations of the electrons in the higher energy state more than the lower ground state. So here in this graph, we can see that as soon as that photon strikes that atom, so it excites to that higher energy state, and as this higher energy state, suppose this E2 has a lower lifetime, and in that case, it falls back to this metastable state. This is the third layer. This is a three-level laser. So in that case, that electrons accumulate here. In this, due to this process, that the electrons accumulated more than to this than the ground state. And during this process, as the lifetimes is goes on decreasing, and it emits more during this process. It strikes more atom during this process, and it emits emits energy. So as you see, when one from this figure, I'll play a video. I think that will be more clear. I think I'm not able to play this video. So this is how this population inversion takes place, and this how is very crucial for the lasing to happen. Uh, So yeah, so like the thing is that what is this electromagnetic spectrum? So what are the different wavelengths that this because of these lasing operations, what are the different wavelengths that we get to see? So as you see from this chart here, we see that from the visible wavelength, that's nanometer, 440 to 700 nanometer. These are the visible wavelengths that we see, and beyond that, that is not visible to our naked eye. So there are infrared, far infrared, and other higher spectrum. So what are the different types of lasers that actually generate these wavelengths? So if we see that in the near infrared regions, the diode lasers like around 980 nanometer ND-YAG lasers. So for mid infrared, erbium YAG lasers, holmium YAG lasers, and all these CO2 lasers and all these things. So these are the lasers that are available to produce different laser wavelength. So moving on, what are the different types of lasers? So, so the lasers are classified mainly into four types: the semiconductor lasers, mostly laser diodes; solid-state lasers based on the iron doped crystals or glass; fiber lasers based on optical glass fibers, which are doped with some active laser active ions in the fiber core; and four is the gas lasers like helium neon lasers, CO2 lasers, argon ion lasers, and excimer lasers. So these are the semiconductor lasers, and these are here in this image we can see. Sorry, the fiber lasers. So the question is like how these lasers are operated. So lasers differ not only with respect to the wavelength of the light, they produce, but also the optical power and the manner in which the power is emitted. So there are different modes of operation of these lasers. There's like the continuous wave, pulse, giant pulse, and mode log. So this continuous wave, a laser that produces a continuous output, so that we can see that is output is a very continuous form, and the pulse laser is that produces a single or sequence of very repeatedly pulses. The pulse length will be like 1 microsecond to 200 microsecond, more than that. And the giant pulse laser that produces very short pulses from 1 nanosecond to 1 microseconds. And lastly, the Mortlock lasers, which produce less than that ultra short pulses like picosecond. Picosecond is almost around 10 to the minus 12 or and like that. And the pulse length is around less than 1 nanoseconds. So the laser safety classifications, like uh, what are the classifications of the lasers? Means like, are they safe or are they harmful? So based on that, the lasers are classified basically into 4 types. The class 1, this class of laser diode does not produce dangerous radiations. No need for any protective equipment. The second class is the class 2, which produces the laser power output up to 1 milliwatt. Typically laser pointer, that is we see mostly teachers use in the classrooms in most countries. The class 3 lasers, 3R, or they produce up to like power up to 5 milliwatts, the maximum power for legal laser pointer in the US, United States. And this type of lasers is generally used for various applications also. So class 3B, this produces 500 milliwatts, moderate to serious eye hazards. Class 4, 500 milliwatts or more eye and skin hazards. So if you see from this image below, there's a class 2, class 3R is classified here, and this image is for mainly from taken for from visible lasers point of view. And this is how we need to see how dangerous the type of lasers are. Actually, it will be marked in the lasers where what class its laser is, and based on that we need to take precautions as per the classifications. So moving on to the applications of lasers. So where do we apply this laser? So broadly, it's classified into 2 types. So based on the wave or particle characteristics of light, the dual nature of light, and this wave-based properties results in interference, diffraction, reflection, refractions, etc. And particle-like properties are based on the light scattering. So the scattering is like why the sky is blue kind of thing. So I think more, that might be people wonder on that. So and then the second category is like governed by the light matter interaction characteristics, starting from simple linear absorption to the very concept of lasing actions. So some very specific application areas like optical communications and storage, laser machining and cutting, military and defense applications, meteorological, geophysical, biomedical imaging applications, or like I think many people have heard about that laser eye operations. Also, there are various applications where lasers are used. So these are some of the applications here where typically for types of sensors where laser is used for like the laser distance sensors, displacement sensors, laser-based trace gauge sensors, laser light curtains. So we see from this image here, this laser fluorescence sensors where we can detect the oil spilled in a real time. So this is one type of sensors that where laser is used. And another from the second image is the laser distance sensors. I think mostly used in the automobile sectors where it's very gaining popularity as a lighter light. That is the most coined term in today's autonomous vehicles. And third image is the laser-based trace gauge sensors, where laser is used to sense the different types of gas in the environment. So today I will be discussing little in detail about the absorption bias gas sensing, where we use the tunable laser. So what actually is this tunable lasers? We have heard about different types of lasers, but this type of lasers is that it's the laser wavelength can be tuned or altered in a very controlled manner. Suppose I have a central wavelength of around 1550 nanometer, and I want to tune the laser, and I want to operate these lasers in a different wavelength. So I can tune the laser with current injections or by temperature control of these lasers. So this type of lasers have very narrow optical line width, which is less than around 200 megahertz, and and for applications like where we require to sense gases. So this type of laser is very frequently used. So how these lasers are used for gas sensing? So as we see from this image here, this is the absorption line of methane, and between 1 micron to 3.5 micron meter. So it's around in the from the near infrared to almost far infrared region, mid infrared region. So like every gas has a very unique absorption lines. So and like just human DNA. So based on that, we uh, have to tune the laser targeting that particular absorption lines. So suppose we want to target this 1.5 or 1.4 micrometer absorption lines of methane. So in order to do that, we need a laser that is have a particular wavelength, central wavelength around this wavelength. So this is the basics of this absorption, how absorption gas sensing, how we use tunable lasers. So I'd like to go into detail, like as I mentioned in my previous slide, this is what it is. How can we sense these gases? So the gas absorption profiles actually looks like this, as I see from this graph. And the laser line width is very narrow, like as I mentioned before in this previous slide, around 2 megahertz, less than 2 megahertz. So what we do is that we target that absorption line, and we tune across that particular absorption line with the help of by changing the laser wavelength, and and scanning across this particular absorption profile. So when we tune across this, we see that as per the Beer-Lambert law, I think most of the students have heard about the Beer-Lambert law, which is it depends on the intensity. So if there is a particular absorption, and if that matches with that particular light, it attenuates. So we measure that attenuation of light as it passes through the particular gas molecules. So this laser is so very narrow that we can tune across this particular absorption profile more than 10 times. So just imagine, like, how small the line width of these lasers is compared to that gas absorption lines. So as we see from this picture, here is the conventional light sources spectral width is so broad. But when we see that, we compare with the laser spectral, is very narrow, very narrow. So just imagine, like, how we can target this absorption lines. So as you see from this fourth image, this is a laser, and this is a particular chamber where the gases are brought in, and we shoot the laser, and accordingly as that the laser passes through this chamber, and the gas molecules interact with that laser light. And there is there's a concept of light matter interactions, and as the particular laser wavelength matches with the targeted gases, so there will be an absorption. And because of this absorption, there will be attenuation of that light that is coming out from that this chamber. So this attenuation of lights give us the concentration of the targeted gases. So now the question might arise is, like, how this optical light is converted into concentration and other concepts. So basically, this whole optical signal is converted to electrical signals with the help of a for photodetector, and this photodetector converts the optical signals to electrical signals, and these electrical signals are processed further with the help of different instruments like digital storage oscilloscope or lock-in amplifier to process those signals and depict the concentration of the gases. So some of that laboratory instruments or items that we require for sensing applications, like to characterize the laser diodes. This is optical spectrum analyzer. So to see what is the particular laser wavelength that it is emitting, so we need to see that, and in order to do perform that characterizations, we need this special, very highly sophisticated instrument called optical spectrum analyzer. And the second is the photo detector. So this converts the optical signals into electrical signals. And the third is the digital storage oscilloscope, or shortly DSO, and which can be used for signal processing and analyzing of signals. And this is the optical fiber that I think mostly many people have seen optical fiber used in telecommunications or in various applications. So this is one of the items that is very crucial for sensing applications also using laser. So I think I have completed my presentations. So thank you.
Thank you so much, sir.
Yeah.
So now I'd like to open up for the question answer session. If anyone having any questions, they can ask.
I think my audio is breaking. Like I'm not able to hear clearly.
So might be here connections are weak. Sir, there is one question. Am I audible, sir?
Yeah,
Hello?
please. Yes, please.
Yes, sir. There is one question. What kind of lasers are used in the laser shows?
Oh, that's a very nice question. So that's a kind of visible lasers. So we see that as laser shows, we see different kind of lasers, like red, green. There's a different wavelength. So I have this different kind of lasers and their application areas, where you see that they're used in different applications. Not only like suppose this laser source there have a particular wavelength, like around green lasers we see that are used not only for only the laser source, they're used for different applications also. Like for spectroscopy, we used to use these dye lasers, and for like the lasers that we see in optical discs, recording lasers or pointers, solid state pumping, SNX. We use semiconductor lasers, so we have this allium gallium indium phosphide, and this type of different lasers are used for different applications. But yes, if we speak about the visible lasers, red, green, blue, all have different wavelengths, and they are normally have different types of applications, not only in types of laser source.
Okay. So the another question is, what are the laser applications in laser surgeries?
Okay, so generally, as you see in this laser surgeries, this gas lasers, that's excimer lasers that is used. If you see from this uh, graph, which have typically output power of around 10 watts or something, very high power lasers. So that have different applications also in the lithography, laser annealing also. So this type of lasers, gas lasers, are used basically for these laser surgeries and operations. Or if you see that in terms of kidney stone removal dentistry, we use these solid state lasers also, which have around the laser wavelength around 2.1 micron or something, 2 micron lasers. So these are for different laser applications for medical purposes.
Okay, sir. So another question, do we need another question from Vikas. Do we need pulse laser or CW laser for sensing purpose?
See, that depends on what is your targeted object of sensing. So generally, if I speak about the gas sensing, where we can use this continuous laser also, but we do use pulse laser also for sensing purpose.
So we have Rajveer Kaur in the meeting if she wants to ask a question. Rajveer, you can ask your question.
Good afternoon, sir.
Yeah, very good afternoon.
Sir, before 1960 लेजर डेवलप नहीं हुई थी, तो तब हम इंटरफेरोमेट्री के लिए कोई लाइट सोर्स यूज करते थे, तो उसके लिए कोरेंस लेंथ कैसे की बात करें तो
Can you repeat that question?
ओके सर, बिफोर 1960 जब लेजर डेवलप नहीं हुई थी, उसके पहले भी इंटरफेरेंस और इंटरफेरोमेट्री का काम चलता था.
Yeah.
तो सर तब तब कोई कोरेंट सोर्स नहीं था, क्योंकि अभी तो लेजर कोरेंट सोर्स सब तो यूज करते. तब कैसे वो इंटरफेरोमेट्री का करते थे, कि क्या यूज करते थे, कि कोई जो सोर्स वो लेते थे उसको कोरेंट कर लेते थे?
See, means like before the discovery of laser, so people might have used different like this experiment. If you see the Young's double slit experiment and all these things, we did see the sort of basics of how we narrow down our sources. So after the discovery of this laser, that's how things have evolved, and it has made into better. So that's what I infer from your question.
Okay, sir.
Okay, so one more question. Do we have a pulse laser in CSIO?
Pulse laser, I am not aware, but we do have CW lasers here at CSI.
Okay. If anyone wants to ask any other question, they can ask.
So one of the thing that yeah.
Yes, sir. Yes, so, sir, is it completed?
Yeah, please.
Oh, okay. So I don't think, sir, we have any more questions. And thank you so much, sir, for your lecture.
Yeah.
I would like to thank everyone, science teachers and school students, to join our webinar. You can further ask your questions going to the YouTube channel CSIR Jigyasa by posting in the comment section. If you're able to answer, we can definitely answer in that. So thank you so much, sir, for your precious time. Thank you, everyone.
Yeah, thank you. Thank you.
Thank you, sir.